Hi, so today we will learn about magnetic field and a magnetic field created due to a long current carrying conductor. So what is magnetic field? Some influence of a current carrying conductor is there all around its space. That influence due to which when a compass needle is placed in this field, that is deflected. That influence is called magnetic field. Or second way. So magnetic field is firstly created by a current created by a current carrying conductor, or if a magnet is there, then all along the magnet you will feel influence of this magnet. When you bring any compass needle near to that, it will be get deflected. And that influence of this magnet all around it, that strength of this magnet all around it is felt at each and every point, and that strength is expressed in terms of magnetic field. So magnetic field is created by two things, either your magnet or a current carrying conductor. Now let us try to define magnetic field in terms of this compass needle, in terms of the force the compass needle experiences when it is placed over here, or when a moving charge is there, moving charge in this field, moving charge, then it will also experience some force. So let us learn. Suppose here you have a magnetic field. Here you have a magnetic field. Okay, let me change the direction of magnetic field. Here you have magnetic field in this direction. And a charge Q is moving. B is along this direction. Q is moving with velocity V in this direction. Then the charge will experience some force and it will make a circular path. When the angle is 90 degree in the direction of magnetic field and in the direction of the velocity of charge, moving charge, then you will find that the charge is executing a circular path. And if, second case, if the direction of the velocity of the charge is not at 90 degree, it is making some other angle, it is not at angle 90 degree, then you will observe that it is executing a helical path, a path similar to a spring. So obviously some force is acting when a moving charge enters into any field. So the strength of field B can be expressed in terms of the force the charge is experiencing when it enters into that field. So the force due to magnetism, force due to this magnetic field can be understood. Force on what? Force on this very charge, moving charge. If the charge was at rest, it will experience no force. Q at rest has no force or will experience no force in magnetic field. Point to be noted. So velocity is must. When a moving charge goes into a magnetic field, then it experiences some force. So force must be proportional to velocity, because zero velocity, zero force the charge is experiencing when it enters into field. So more velocity, more force will be there on this very charge. So force is proportional to velocity, one thing. And obviously force, if you put some logic, so you will find that greater the charge, greater is force. Force is proportional to charge also. And force is, similarly you can find that proportional to magnetic field. And here you can see, changing angle, the way of experiencing force is changed. So force is also found to be proportional to sine of angle between velocity of charge and magnetic field. So if this angle is theta, so okay, here you have theta along this direction of velocity and direction of magnetic field. So it is also proportional to sine of angle between the direction of velocity and direction of magnetic field. So when you combine, this is also called actually Lorentz force. So I will be doing Lorentz force in different lecture, but this time I am defining magnetic field in terms of force. So F is equal to QVB sine theta. Therefore, B is equal to F upon QV sine theta. So what is magnetic field? Magnetic field is force experienced by a moving charge in any magnetic field a unit charge, because it is in denominator, so by a unit charge moving with unit velocity. Per unit angle bit sine of angle between velocity vector and field vector. Velocity and field vectors. Okay, this is how you will be explaining magnetic field. You cannot say that magnetic field is the space all around a magnet, because space has unit of volume, that is meter cube. So magnetic field cannot be defined as the space all around a magnet. Yes, you can say that the influence in the space all around a magnet is defined by magnetic field. The influence all around a magnet and it is different at different points. In a space which is location specific and which is location means at different locations field is different. Is used, okay, defines the magnetic field. So this is the magnitude of magnetic field. Now magnetic field has SI unit. Magnitude has SI unit, Tesla, and CGS unit, Gauss. Now 1 Tesla is equal to 10 to the power 4 Gauss, and you will be amazed that Earth's magnetic field has strength B is equal to 10 to the power minus 5 Tesla, such a small value. So Tesla is not very useful unit, it is a very large unit. So we generally use Gauss in place of Tesla. Gauss is a convenient small unit. At many a place you can find written that magnetic field is the space all around. But space all around a magnet. But space has unit meter cube. And space all around a magnet cannot be the definition of magnetic field. Yes, it is the property of some property of space all around a magnet, and due to which a force acts on any moving charge when placed there. So what is magnetic field? Magnetic field is equal to force acting per unit moving charge. And it also depends on its velocity, and it also depends on the angle, sign of angle between velocity and B itself. Now since it is a vector product of two vectors, so force will be perpendicular to both. Force will be perpendicular to both V and B. Since vector product of V and since F is equal to Q V cross B, therefore force is perpendicular to V is perpendicular to B, and its direction can be found by a right hand screw rule. Direction can be found by a right hand screw rule. Okay. So actually I was interested in definition of magnetic field only. So what is magnetic field? Force acting per unit moving charge, per unit its velocity, per unit the sign of angle between V and B. And you should not say that magnetic field is the space all around a magnet, because space has its unit meter cube. It is so it cannot be the definition of magnetic field. So do remember magnetic field in this way. Now magnetic field due to straight current carrying conductor. Assuming Biot-Savart's law. So let there be a current carrying conductor carrying current I. Let carrying current I. So we need to specify every symbols that I am going to use. Let there be a length element of length dl. dl vector, length element. And from this length element, let me change the color so that it could be seen. And from this length element at a distance r, at a point P, we have to find magnetic field. Okay. At a displacement r, vector r, at point P, we are to find magnetic field B due to whole current carrying conductor. Okay, so let us draw a perpendicular which meets the current carrying conductor at O. So I am not going to write everything, so that time is very important. We should not write everything. Just let us see in picture only. So let me draw a perpendicular which meets current carrying conductor at O, and this perpendicular distance is A. Now, if angle between displacement vector and this length element is theta, okay, and it is making angle phi along this direction. So if you long straight, okay, it is a long straight current carrying conductor. Let me rub this. You have this okay. This is a long straight current carrying conductor. Here you have a length element, and here you have a perpendicular of length A, and from origin it is at a distance L. This length element is at distance L from origin. The length element dl is at a distance L from origin O. Now using Biot-Savart's law, we know that magnetic field dB due to length element, or better I should write current element, because field develops due to current element, IDL. Okay, length element into I. This is called current element. This is the source of magnetic field. Is dB is equal to, using Biot-Savart's law, we know that mu naught upon 4 pi IDL sine theta upon r square. So when you integrate this dl with proper limits, then you can find magnetic field due to whole current carrying conductor. So let this lower tip meets, and it is making phi 1, and at point P, the upper tip is making angle from this perpendicular line phi 2. Okay, so everything I have described in figure itself. So now let me convert this dl, this sine theta, r, everything in one term so that you can integrate in a simple way. Because so many variable things are there, then integration becomes difficult. Here theta also is varying, L also is varying. So let me convert everything. This R also varies. As you go on near to origin, R goes on reducing. As you go away from origin, R goes on increasing. So let me convert this single thing, variable thing, into one term. So okay. Now in triangle, which triangle? Right angle triangle, OP and OP, okay, here I should take Q, one more point, in triangle OPQ. So tan theta is equal to sine theta. Okay, let me write in terms of tan phi. Tan phi, that will be more helpful. Tan phi is equal to perpendicular, and the perpendicular is L in this case. L upon base is a, this base is a constant, because for that point, for taken point P, the distance A is not going to change. So therefore L is equal to A tan phi. On differentiating, with respect to d phi, with respect to angle, okay, with respect to phi, तो हमें क्या मिलता है जैसा देख लें. dl upon d phi is equal to, A is a constant, and d tan phi upon d phi, therefore dl upon d phi is equal to A sec square phi, therefore dl comes in terms of A sec square phi d phi. So one thing I obtain, one thing out of all these things, okay, dl I obtain. Now let me find sine phi and r square. Now sine theta is equal to cos 90 minus theta. And in this right angle triangle, you can see this is already 90 degree. So if it is theta, then phi will be equal to 90 minus theta. So cos sine theta is equal to cos phi. Sine theta is equal to cos phi. This is the another piece of information that we'll be using. Let me name it equation 2. This as, okay, name this as equation 1. This as equation A. This as equation B. Now next thing is r square. So in place of r square, okay, so using the equation, since cos phi is equal to base by hypotenuse, base A by r, A upon r, therefore r is equal to A upon cos phi, therefore r is equal to A sec phi. So three things we obtain, and we will be putting the value of A, B, C in equation 1. Now on putting values of A, B, C in 1, we get dB is equal to mu naught upon 4 pi, and then I in place of Tn, A sec square phi d phi. Ideal sine theta, in place of sine theta, cos phi upon r square, and in place of r square, A square sec square phi. So sec square phi is cancelled, A is cancelled, therefore dB is equal to mu naught upon 4 pi I upon A cos phi d phi. And now we need to find value of magnetic field. So let me integrate this magnetic field under the proper limit. Here everything now has changed into a constant. A, perpendicular distance, is a constant, current I flowing is a constant, and the variable thing is angle. So let me take the limit of angle from minus phi 1 to plus phi 2. On integrating dB under proper, integrating means adding summation of all the dB due to all the current elements. Okay. Under proper limit means minus phi 1 because it is in negative direction to plus phi 2. So we observe that B, which is equal to integration of dB, is equal to integration of under limits minus phi 1 up to plus phi 2, and the things are mu naught A cos phi d phi. So let me take every constant things outside the sign of integration, mu naught upon 4 pi I upon A, and cos theta becomes sine, cos phi becomes sine phi under limits plus phi 2 up to minus phi 1. Okay. Therefore B is equal to mu naught upon 4 pi I upon A sine phi 2 minus sine minus phi 1. And you know that sine minus theta, fourth quadrant, is negative. Therefore it becomes equal to sine phi 2 plus, because minus into minus plus, because sine minus theta, fourth quadrant, and sine of any angle is negative there, so minus of minus, it becomes plus sine phi 1. So this is magnetic field due to a long current carrying conductor. Now if the length of the conductor is infinite, then phi 1 is equal to 90 degree and phi 2 is equal to 90 degree. Therefore B is equal to mu naught upon 4 pi I upon A, perpendicular distance, into sine 90 is equal to 1 plus sine 90 is equal to 1, and this becomes equal to mu naught upon 4 pi to I upon A. So now I conclude So magnetic field due to infinite long current carrying conductor comes equal to mu naught upon 4 pi to I upon R. So here I conclude.